So welcome to part 2 of series circuits, where I want to unpack the concept of a voltage divider. Now, voltage divider is actually a formula, and it's also a circuit. Okay, so the voltage divider is actually so cool because it's a formula that allows us to really quickly calculate the voltage drop across any one resistor or the voltage potential anywhere in a circuit without like going through multiple steps like we did when we discussed series circuits, where we had to calculate the total resistance or calculate the current, and then from there use Ohm's law to do this in the second step. In this case, we can just do it with one formula. So I've got this PowerPoint here, and let's roll through and talk about voltage dividers. So before we kind of jump into voltage dividers, I want to talk about different kinds of voltage, or this kind of perspectives of how we look at voltage. So we've got voltage drops and voltage potential. Now, voltage potential is kind of like how much voltage we have relative to ground or relative to the negative of a battery at any point in the circuit. A voltage drop is actually just the drop in voltage. Let's just kind of move on a little bit here. In this case, I've got relative to ground is my voltage potential. So how much, voltage is energy per coulomb. So how much energy per coulomb do we have at any point in the circuit relative to ground? Okay, kind of like, if you got to throw something up in the air, right? Well, if you throw it up in the air and you're on a roof and it's just going to fall on the roof, its voltage, that's energy potential is only like, as far as it'll land and then fall on the roof, unless it's a flat roof. Yeah, if you're on a flat roof. But if you're going to throw it off the edge of the roof, then its potential is greater. So when we're talking about voltage potential, we're actually looking at the energy of the voltage that's there, how much work we can do with that to ground, relative to ground. So in this case, let's just kind of jump over here. Now, in this case, I've got what's VRC. So what VRC is here, this is the voltage potential at point C. But it's also the voltage drop across R3. Actually, yeah, it's R3. And the reason is because after we've dropped all the voltage across R3, we've got nothing left. In this case over here, we've got this guy, which is the voltage potential at B. But in this case, it's also the voltage drop across R2 and R3. So I would say that the voltage drop across R2 plus R3. Over here, I've got the voltage potential at A, and that's going to be also the voltage drop across R1, R2, and R3. Now, if we take a look at kind of the voltage drop of things, it's how much energy is lost when those coulombs are being pushed. That energy, voltage per coulomb, joules per coulomb is a volt. And as it's being pushed through a resistor, I'm losing energy. How much energy did I lose? And that is the voltage drop. So here we go. Now the voltage drop across R1 is this. It's the definition is that. So that's how much energy I have lost with those coulombs going through there. The voltage potential before and the voltage potential after are different. And actually, I can calculate the voltage drop with those two voltage potentials. So here we go. I've got VR1 is equal to VA, which is the voltage potential before, and VB, which is the voltage potential after. The difference is how much I have lost, which is the voltage drop. There you go. So ground. This is a symbol that I want to talk about. We use ground symbols for a lot of different reasons. One of the benefits, I think, of a ground symbol, I think ultimately the real reason we use a ground symbol is to save us drawing more lines in a circuit diagram. So let's say I had a whole bunch of resistors that all needed to connect to ground, like directly to ground, in that the voltage drop across each one of those resistors would actually be the voltage potential before them. Not just the voltage drop, the voltage potential before them, because voltage potential is relative to ground. There you go. So in this case, VR2 is also the voltage potential just before that resistor. So if I had a whole bunch of resistors in parallel, yeah, you may not know what parallel is, but we will talk about that next week when we get into parallel circuits. But let me just give you an example. Actually, this ground symbol is used in automotive in like a big way, because the metal of the body is the ground. The chassis of the actual car is the ground, and it's physically wired and connected to the negative of the battery. That's pretty cool. So essentially, any kind of motor or light or switch or whatever that we have, one side of it is actually, the negative side is connected directly to the metal. That's pretty cool. Saves a lot of wiring. Okay, so we can also have that circuit in the beginning that I was showing here, just with ground symbols instead. That's it. So again, just to go over this quickly, just until we so you get it. in case you haven't figured out what I was talking about before. It's just another slide about voltage potential. Okay, over here, just we're looking at voltage potential. VA is voltage potential, VB is voltage potential, and VC. It happens that VC is also equal to the voltage drop across across R3. And VB is equal to the voltage drop across R2 and R3, and VA is equal to the voltage drop across R1, R2, and R3. Voltage drop is just that. It's just the drop. Now, this is interesting. The voltage drop across R1 and R2 is the sum of these, or the sum of the voltage drops across these is going to be this. That's how I say that. I can also say it VAC as opposed to saying VR1, R2, and that's because I've named nodal points on my diagram here. If I didn't have these nodal points named, I'd have to actually call this VR1 plus R2. Now, let's jump into voltage divider. I got a couple more slides left, and then you guys are experts. Let's move forward. Essentially, I need to kind of unpack the idea of dividing voltage. Yeah, the resistance divides voltage depending on what its percentage of the total resistance is, right? So in this case, we've got two resistors here. One is 50 ohms and another is 100 ohms. So you can look at it a couple different ways. One is the 50 ohm is actually 1/3 of the total resistance, okay? And the other is that the 100 ohm is 2/3 of the total resistance. And that ratio, if you just multiply it by the voltage source, then that's how much of the voltage it steals. The other way of looking at it is like this. If you look at that 50 volts, and the 50 ohms and the 100 ohms. 100 ohms is twice as much as the 50 ohms. So it's actually going to steal twice as much voltage. So essentially, if you've got twice as much voltage than the 50 and the 50, that's 3 times the voltage of the 50. So there's kind of the 50 steals 1/3 and the 100 steals 2/3. Kind of a way of looking at it. So you take that ratio, you multiply it by the source voltage, and you have how much voltage that thing steals, or more specifically, how it divides the voltage. So essentially, here's the formula. Really basic formula. Just throw it in. It's really cool. It's the voltage source multiplied by some ratio, and that ratio is ultimately the percentage of whatever that particular resistor you're looking at compared to the total resistance, what percentage of that is. So in this case, it's Vx and Rx. So that X is, you have to put a value in there, not a value, but you have to put something in there. You put, VR1 or VR2 or VR2, R3 or VAB or whatever you're looking at, whatever resistances or 2 points or whatever you're looking at that's actually dividing that voltage. And then you have to actually write that value in here. So whatever voltage you're looking at here, and then the actual resistance that dividing that voltage goes in here. For instance, if I was trying to figure out, the voltage here, I'm going to write VB, and that's VR2. So VB is the voltage potential here. It's also the voltage drop across R2. So I'm going to write R2 because R2 is the thing that's kind of, stealing that voltage. What percentage of the total is it? Well, in this case, it's half because I've got 200 and 200. So I'm going to write R2 here, and then when I fill it in, I'm going to write 200. Here I'm going to write 200 plus 200. It's really simple. If you just write 400 there, everybody knows because 200 plus 200 is 400. But I'm writing it down here to be specific so that you see, this is the total voltage here, the total resistance here. Now, it's important that you put the ohms in here. Dude, if you write a number down in a formula that is a measured value, it has to have a unit. I know that ohms and ohms cancel out because I'm just left with volts. But dude, you have to put the units in. There you go. So this is another situation where we're kind of tapping into the middle of the series circuit. So we're looking at voltage drop here. In this case, in the case before, we were looking at voltage potential. So we're using the voltage divider formula to calculate voltage potential. You could argue that we're also calculating voltage drop. So in this case, we're actually calculating voltage drop, right? We're not calculating relative to ground. We're saying, hey, of these two resistors, 94 ohms and 417 ohms, how much of their total resistance, what's the percentage of their resistance to the total resistance? And then you multiply that by the voltage source and you get whatever voltage they steal or they divide. There you go. I'm filling in the values. So in this case, VBD, so the voltage between here and here, what is that voltage? I'm going to find the ratio, which is essentially their total resistance. In this case, it's R2 plus R3, so 94 plus 417 divided by the total resistance. I'm just filling in the values, and these brackets are helping me do that. And I'm going to put my units in, and then I press play, and I got 5 volts. There you go. Now, I want to put this into a potentiometer. Potentiometer is really cool. The voltage divider formula allows us to calculate the voltage that comes out of a potentiometer. We talked about potentiometers, I think, in week 2. I think I'll talk about pots as we go throughout this course a little bit more. But in this case, what I'm saying is that the total resistance in this pot is right here. It's from pin 1 to pin 2. That's the total resistance. And then pin 3 kind of taps into that along the way. It's called the wiper. Pin 3 is the wiper. So what we're doing is we're kind of tapping in, and we're creating two different resistive values that are kind of moving up and down. The total of them is always whatever the pot is rated at. And we can see here, if we kind of divide them into 2 here, we can see this 0.3 is in the middle. So it's almost like 2 resistors here. Let's actually look at this very last slide, and we'll just have an actual example. In this case, I've got a pot. This is a symbol for a pot right here. We draw a resistor, and we put the wiper in there, and then that's the pot, actually. And then we're done. That's how you draw a pot. So in this case, what I'm looking at is I'm looking at a situation where I've got a 600 ohm resistor, or the internal resistive strip in the potentiometer is 600 ohms. I've turned it 1/3 of the way. If I tap into that point B, or that point, actually 3, this is point 3 here. So if I tap into point 3, I've labeled it B here, and I want to study the voltages across my pot, then I can just use the voltage divider, because what I've got is I've got now kind of 2 resistors inside that are connected in series together. And one resistor is going to be 200 ohms, and the other resistor is going to be 400 ohms. That is if I've turned it 1/3 of the way. So if I wanted to do the math and find out, hey, what's the voltage drop? Actually, the voltage drop in between point A and point B, I could calculate that. I could just use the voltage divider, and I could say VAB is RAB, whatever that resistance is, because we know it's 1/3. It's going to be 200 ohms. And then over here, I've got the total resistance of the pot. So the total resistance of pot 1, so that's 200 divided by 600, multiplied by the source voltage, 30, and I got 10. And that makes sense, because 10 is 1/3 of the source voltage, and I've got my pot turned 1/3 of the way. If I wanted to know the voltage potential, yeah, our first one was actually calculating the voltage drop in between point A and point B. If I want to know the voltage potential, I could use Kirchhoff's voltage law for that, and I could say, well, it's whatever we have left. We've lost 10 from point 1 to point 2, or point A to point B. We've lost 10 volts, so it's 20. But we can also calculate it just by jumping in right into the potential on the voltage divider formula. And what I'm going to say is the voltage potential at point B is the voltage drop across that section, that last section. So how do I name that? I don't know. RA ground? I mean, RB ground? That's what I've called it here. RB ground. So that's that section of the resistor divided by the total resistance of the pot multiplied by the source voltage. So it's 400 divided by 600 equals 20 volts. There you go. So thank you for watching this quick lecture on voltage dividers. Voltage dividers are really cool. What I need you guys to know is just that, this is actually will get really simple. If you do 1 or 2 of these examples, you'll be like, okay, this makes sense. Whatever, this is easy. At first, it may not be perfectly easy, but once you get like 1 or 2 through, you'll be like, okay, actually, this does make a lot of sense to me. I think you'll be good. Now, I need you guys to wrap your head around that, because when we get into series parallel circuits, when we actually put really complicated circuits together, the voltage divider formula is also really powerful, but it gets a little bit more difficult to use it when we get into that. So wrap your head around this now, so that when we get to series parallel circuits, you'll be an expert. That's it. Oh, goodbye.